Hi, I'm Laura McCann and I'm a first-year graduate student here at the Cyclotron Institute. Astatine-211 is an isotope of interest for many isotope production facilities because it shows great promise for targeted alpha therapy cancer treatment. Its short half-life of only 7.2 hours makes it a good candidate for biological systems, but it also poses some challenges for hospitals to gain access to it for research and medical use. It's currently produced via the alpha-2N reaction on bismuth-209 via a 28.8 MeV alpha beam, limiting the number of facilities capable of producing astatine. Texas A&M University has recently joined the University Isotope Network of the Department of Energy's Isotope program to increase the availability of astatine-211. A major challenge of using a bismuth target for this reaction is its relatively low melting point, which is also near the boiling point of astatine. Should the beam deposit enough energy in the bismuth target to melt it, it is possible that the astatine could become volatile, so target development has been a key component of our isotope production program. We make our targets by melting bismuth on a hot plate inside of our target frame, and from there have tried both spreading the molten bismuth into the target with a spatula and pressing it down with a stainless steel weight. In both cases, there is a colorful slag that forms on the surface immediately after the bismuth is heated. We are currently in the process of determining if this is due to impurities in the bismuth or oxidation caused by the heating process. For the targets made by spreading the bismuth with a spatula, the slag is removed from the surface with the spatula and the remainder of the bismuth is spread around using the spatula and tipping the target to roll the bismuth into the edges of the frame, which has produced nice results. For the weighted targets, the bismuth was melted and a weight was placed on top of the bismuth in an effort to spread it around and create a thin layer. This resulted in the weight becoming stuck to the target, so future tests contained a piece of aluminum foil between the weight and the bismuth. However, in all cases with this weighted method, some of the bismuth sticks to the aluminum and it never fully spreads around into the target frame. In order to make the surface more uniform and to look for impurities, some of the targets were machined as shown here. This also helps make the targets thinner, which will hopefully deter melting. Fred Abelgan, a member of our operations staff, has an ultrasonic soldering gun that we are currently testing as a possible option for making even thinner targets. In order to avoid the melting of our targets, we are aiming to dump most of the beam energy into the aluminum frame rather than into the bismuth. For this to occur, the optimal depth of the bismuth on the targets is 70 microns. While the cyclotron has been under maintenance, we have developed a new target apparatus that eliminates an additional interface between the chilled water flow and the back of the target. This image shows the chilled water coming up through the back of the new flange into the center of the target and flowing back to the chiller around the outside of the target. In order to test the effectiveness of this chilling mechanism, we applied a high heat using an industrial heat gun to the center of the target and measured its temperature with and without the chilling mechanism. Without the chilling, the target frame reached a maximum temperature of 145 degrees Celsius, while with the chilling mechanism, it never broke 60 degrees. While we could not get the heat gun hot enough to melt the target, even at its highest setting, it demonstrated that the chiller is making a large difference in the temperature of the target. After we irradiate the target overnight, we take it to the radiochemistry lab, which Steve will tell you about next. After the separation, we get a characteristic astatine-211 X-ray and gamma spectrum like the one shown here. The astatine-211 gamma ray is at 687 keV, and its daughter polonium-211 gamma rays are at 569 and 897 keV. Additionally, the first unlabeled larger peak is 511 keV, and the second is 1039 keV, which are probably due to minor contaminants in the target.